Hello, hello. Yes, it is the classic restart, absolutely. Oh, good, my audio's fine. Nice. Yeah, I still haven't fixed that problem where I have to restart. Um, but yeah, oh well. Hi, Sly, good to see you. Hello, CJ as well, good to see you too. Yeah, I'm doing okay, pretty good. Glad to be back talking about physics, hopefully. um, So yeah, as I guess you can kind of see on my screen, I wanted to talk a little bit about quantum tunneling, like you mentioned. Well, I guess it's like a month ago now, which is pretty crazy how long that has been since you submitted that question. Um, but yeah, so we haven't been streaming for 3 weeks, which is quite a long break. But as I put on my Discord, I wasn't in my room because of a family stuff. But now we're back, so hopefully we'll try and stick to a slightly more regular schedule than the last few weeks. But that should be fine. What was with the break? Well, the break was I wasn't home. I wasn't here. I had to go back to be with my family for a little while because we had some really quite sad news. That I won't go into at the moment. But yeah, now we'll be back regularly, I hope. So, I mean, as usual, obviously this is the office hours, so it's, if you've got questions, just pop them in the chat. I've got a couple of things I thought I would talk about um, beforehand, uh, before any other things come in. Um, First, quantum tunneling, because Sly asked me to talk about it like a month ago now, um, and we just haven't quite got around to it. But no, hopefully we can talk about it a bit. I didn't manage to look at because when I first got sent this question about quantum tunneling, I got sent loads of really interesting looking papers and references, and I'll be honest and say I didn't have time to actually take a look at most of them. So I won't be talking really about. I think the more interesting thing that Sly was interested in that's kind of this superluminal quantum tunneling, or rather, talking about why actually it's not superluminal. There is no superluminal quantum tunneling. I don't think there's any evidence of that, and it certainly wouldn't be something anyone would expect to see, because it would, violate relativity in some way. Yeah, no, they did look interesting. Thank you for including them. I will definitely take a look at them. Um, but I suppose I'll give a kind of quick, sort of not too advanced look at what tunneling is, from the perspective of the Schrödinger equation, which is, one of these quantum mechanical equations that is kind of like the Newton's second law of quantum mechanics. Um, Newton's second law tells you if you've got forces acting on something, you can compute things. Well, you can immediately find the acceleration, and from that, you can compute things like velocities and positions. Often it might be quite difficult to do so. You might end up having to solve a fairly challenging differential equation, but the ingredients are there. And likewise, the Schrödinger equation contains the ingredients for understanding the dynamics of quantum particles, or the mechanics of objects that are very, very small, such that quantum effects are, the dominant thing on them. They're governed by quantum mechanical laws of motion, and the Schrödinger equation is the equation that governs the dynamics of non-relativistic particles, on a very small scale at a kind of quantum level. Um, so sometimes, I mean, it's very possible that if you're doing stuff with the Schrödinger equation, because it's not a relativistic equation, things might appear to come out that look like they violate special relativity. You might get things that appear to give things traveling faster than the speed of light. The same way in Newtonian physics, if you don't include special relativity, Newtonian physics very, very often and very straightforwardly can give you velocities greater than the speed of light. physically these things don't happen, but because Newtonian mechanics does not contain relativity in it, these things will appear mathematically, although physically they correspond to a breakdown in the validity of your equations. And similar things can happen with the Schrödinger equation, because this is not a relativistic equation. It doesn't have programmed into it the fact that things should travel not as fast as the speed of light. But I don't think that's quite to do with what this superluminal tunneling stuff is. I think that is actually a little more complicated, how some of these things appear to be transmitting stuff faster than the speed of light. But I think this is not a real effect. I think it's it's a bit of a fake thing, like an apparent effect, or sometimes these things are kind of got away with, like in the case of entanglement, where it sort of appears that if you have particles that are entangled with one another, this means that, the quantum state of one is tied to the quantum state of the other. So say you start off with two particles in like a singlet state. So you've got two particles, one could be in spin up, one could be spin down, but you don't necessarily know which is which. And then but you know that one of them will be up and the other will definitely be down. This is kind of what it means to be entangled, that the specific quantum state of one will determine the specific quantum state of the other. And if you separate these things to very great distances, and then you measure one of the particles' spin, in sort of measuring for yourself one of the particles, say it's measured as spin up, well then you've kind of confirmed to yourself that the other one is spin down. But because of quantum mechanics, quantum mechanically, it's not as simple as, you could think of a classical sort of analogy that appears to be the same as this. You could say have two identical sealed boxes, and in one there's a red ball and in the other one there's a blue ball, and you could shuffle these boxes between you and a friend, and then you could travel to opposite ends of the galaxy, over a very long time. And of course then if you open your box and you see you've got a blue ball in there, your friend's got a red ball. So you might think that is a bit like what quantum entanglement, this thing I've just described, is saying, but actually they're very different, because it's not predetermined. When you measure your electron, your entangled particle, whatever it is not predetermined whether it will be spin up or spin down. It's only determined when you make the measurement. So it seems to be that there is some apparent transmission of information. There isn't, in actuality. It's not quite like that. It appears that there is some transmission of information whereby when you measure the spin of one electron in your half of the galaxy, and you see it as a spin-up electron, it then appears that, well, therefore, in me measuring my electron as spin-up, I've determined that the electron on the other side of the galaxy that my friend has is spin down. So I have obtained information about that electron which I could not possibly have had prior to my friend and me zooming off to opposite ends of the galaxy. I've obtained information about the state of that electron. So this appears to be information traveling faster than the speed of light, but you kind of get around it in relativity by saying it's not really useful information. It's not information by which you can transmit anything. I mean, it's not even really information in that sense. It's not something you could usefully transmit anything. You couldn't send an encoded message. You couldn't do anything like that with this. So there are some ways that sort of it looks like in quantum mechanics that you get this superluminal stuff, or stuff traveling faster than light, but actually it's not really like that. You don't really get any of this, any superluminal transfer of useful information, or indeed in tunneling particles traveling faster than the speed of light. But it appears that they do. That's kind of what it looks like on the surface, but it's not quite like that. Oh, good to see you too, Rooster. Thank you. Yeah, hopefully we'll stick to the usual schedule from now on. Though actually I should say I won't be doing this Saturday. I think what I'm going to do now is I'm going to have to do like every second Saturday is I will stream, because from now on, now the lockdown in the UK has lifted a little bit, I can sort of socially bubble with my family's home in Essex. So every other weekend I'll be going back home to see to see them, well, to see my mum. So I won't be here this weekend, but then the weekend after, on Saturday, then I'll do another Saturday stream, possibly a spacewalk or something, one of these sort of slightly longer, slightly more focused ones, other than, distinct to the office hour. So that's kind of just a bit of a ramble about quantum mechanics and why it doesn't really give you anything superluminal. But like I said, I'm not really going to be talking about superluminal stuff or apparent superluminal stuff for the most of today. I just want to talk about starting off, hopefully with the intention to come back to tunneling in a slightly more detailed way sometime later on. But for today, I just want to talk about quantum mechanical tunneling from the point of view of the Schrödinger equation. So non-relativistic quantum mechanics. And of course, because I don't have a death wish, I'm simplifying this and considering it in 1D. Because anything bigger than 1D you generally would have to do, unless you've got some extreme symmetries, you'd have to do numerically, and I don't feel like coding today. So we're just going to do it in one dimension, Schrödinger equation, so non-relativistic, and I'm going to try and gloss over some of the detailed algebra because it's not particularly fun, but it's it's important. But I don't want to talk about it too much. A slight tangent. Were you excited to hear about G-2? I was indeed. Yeah. So I'm definitely going to talk about muons after tunneling. That's something we'll speak about both of the muon results because there are two of them. There's the RK one that came out 2 weeks or 2 or 3 weeks before the G-2 one, and then there was the G-2 one. So the muon has had a pretty busy month or so. And both of the results are really interesting. I think I'm more excited by the RK result, which is about the decay of B mesons to K mesons in measuring how the weak force couples to leptons, how it seems to couple slightly more so to electrons than it does to muons. There's a difference in the coupling strengths between them. Personally, I think that's a more interesting result. But we'll talk about both of them because they are both really fascinating. Hi Yang Yang, good to see you too. But let's talk about tunneling a little bit first. So as you can see here, I've written down the Schrödinger equation in 1D, which I described earlier on as being kind of like, Newton's second law for non-relativistic quantum mechanics. It's this equation that gives us all of these dynamics of quantum mechanics. It tells us how things evolve with time, how they behave in that way. And now the setup I'm going to consider is a barrier potential. So this is a steep wall here, then a flat roof up here, and another steep wall down here. So I don't know, you might not be able to see that. You might have to turn your head to the side, but I've just labeled the positions that this wall has. The center of the wall is x equal to a, and then I've got a minus w over 2 and a plus w over 2. So w is the width of this wall here. That's a rubbish arrow, like that. Okay, that's a slightly odd message. Well, not thank you, actually. That's kind of weird. Never mind. So we have this potential setup that I've denoted in red. This potential barrier. So in red is the potential that this particle is confined in. Green shows the energy of the particle itself, this quantum particle as it's coming in. Here is what I've called, there shouldn't be an L there, I changed my notation midway through and went back to it. So psi here, I should have also explained actually when just talking about the Schrödinger equation, in case some of you haven't seen the Schrödinger equation before. This quantity psi that appears in the Schrödinger equation is what we call the wave function. So quantum mechanics, has a lot of analogies to kind of the physics of ordinary waves. You have phenomena like superposition, fundamentally quantum mechanics, is all about probabilities. And this quantity psi that I've called the wave function is related to probabilities, the likelihood of you measuring something in quantum mechanics. Specifically, psi is related to a probability density in space. So psi tells me, or rather, psi is related to something that tells me how likely I am to measure an electron, or whatever this particle is, between, say, this point and this point. So to measure it somewhere between here and here. And the way you get from the quantity that appears in the equation, psi, to the physical thing you would measure, say you set up hundreds and hundreds of these experiments and you, measured lots of different positions along the line to try and experimentally construct a probability distribution for how likely you are to measure the electron in a certain position. That experimental thing, or that the quantity that makes touch with this experimental thing you would measure, is psi squared, or psi specifically, because psi is a complex number, it's psi modulus squared. Quantum mechanics I think is pretty interesting in that imaginary numbers come into quantum mechanics in a way that is really totally unavoidable. So people often, the fact that an imaginary number is called an imaginary number is not really very accurate. They're no more, or rather, they're no less real, real in inverted commas, than any other number, than a whole number, than a fraction, positive numbers, negative numbers. Imaginary numbers, or rather complex numbers, are just as real as these numbers are. In terms of their physical significance, if you think about quantum mechanics as being, a more fundamental law of nature than, or, a set of rules of nature than something like Newtonian mechanics. Generally, you could say quantum mechanics is more fundamental because you can get Newtonian physics out of quantum mechanics. You can actually get Newton's second law out of the Schrödinger equation with a little bit of playing with it. And these laws, the Schrödinger equation, that is impossible to write down without imaginary numbers. So imaginary numbers play an incredibly important role here, and they're just as again, quote unquote, real as real numbers. So there I'm using two kinds of real. I'm using real as in physically meaningful, and I'm using real without inverted commas, meaning, the mathematical definition of a real number, i.e. one that does not have an imaginary component to it. Sly says, the normal Schrödinger equation is complex, right? Because the one we talked about in school wasn't. No wonder you normally take the square of the absolute value of the wave function for the probabilities. Yes, exactly. Yeah, that's what we were just saying there. So the Schrödinger equation absolutely has imaginary numbers in it. You can't really write it down without imaginary numbers. You can write down, I guess, technically, if you're thinking about the time-independent Schrödinger equation, then this right-hand side here is replaced with e times psi. Ignore that dot. There's none of this. So that, I suppose, technically has no imaginary numbers in it. But your solutions will have imaginary numbers for the most part. There will be these complex exponentials. So it's all still impossible to do without imaginary numbers. Okay, so again, the setup we've got is we have this potential well, which is, you can think of this as being a literal wall. You can think of this thing here as being an actual, opaque wall or something that we fire a particle at. In this case, I denote this as like a little wave packet here moving to the right. And the thing that is waving, it's sort of, if we're talking about particles, what is the thing that is waving? Well, the thing that is waving here is the wave function. This is the thing that sort of describes this wave-like behavior of particles. This is quantum mechanics kind of morphs together. You can think of it about light as the most classically obvious example. How Newton was firmly under the impression that light was a particle. He had done lots of experiments that kind of confirmed to him that light behaved like a particle in terms of reflection and all sorts of other stuff. But there are just as many other experiments where light behaves as a wave in terms of diffraction. So light appears unusual in that you can't describe it classically as a particle or a wave. It doesn't quite work out when you call it either one of the things. So really there's something far more complex going on among light and also among every other particle in general, but the most obvious classical example is light. And this is really only solved by quantum mechanics. So, hang on, my internet hasn't died, has it? I hope it's not. Can I still hear myself? Okay, I can still see myself. Never mind, sorry. And this is only resolved by quantum mechanics, which sort of takes these particle pictures, this particle picture and this wave picture, and combines them together. So rather than having light behave purely as a wave or purely as a particle, it kind of behaves as this sort of complex wave given by the wave function, which corresponds to the probability of where you will measure the particle. So this sort of blends the two things together. It's like when you look at something, when you make a measurement of a particle's position, or, you know, rather I should say, when you make a measurement of an electron's position, you will measure it as being at a definite point in space, like a particle. But when you're not looking, or to be more accurate, to not anthropomorphize these things, when you're not making a measurement, when the electron is, you know, behaving and interacting only sort of in an internal environment, not with sort of external interactions going on with it, it will behave like a wave. It's only when you have some observation of it or some interaction with it that this wave function collapses, is the term people use. The wave-like behavior goes away and it appears again like a particle with, you know, a definite packet of energy localized at a single point in space. Okay, so that's a kind of general description of what psi means in the Schrödinger equation and how we're looking at it here. So we're going to look at two kind of instances in time. We're going to consider, well, first of all, I should say what we're doing. Essentially what we're doing is we're firing a particle described by this wave packet here, this little wave function packet thing here. We're firing it at this potential barrier, at this wall that I've drawn in red, and we're going to consider what happens after that, after it has collided with the wall. So before it's collided with the wall, this is why I write before here, the wave packet is on the left-hand side, and we're firing it along to the right, and we want to figure out what happens during and after this collision with the wall. So if you think about this classically, what you were doing classically here, the energy this particle has is given by this green line here. So this is the total energy of the particle before it collides with the wall. Then this potential barrier has a height here that corresponds to an energy, let's call it V0. So we can see that V0 is larger than capital E. So the potential energy the particle would have to have in order to, you know, get on this bump here, to get over this bump, the potential energy it requires is larger than the total energy that the particle has. So total energy, you know, is potential energy plus kinetic energy. For the particle to get over this bump, when it's up here, it will have potential energy V0, but it will still have total energy capital E, because this is its total energy which is conserved. But it can't possibly have E equals to PE plus KE when the PE up here on top of the wall, on top of the barrier, is larger than the E initially. Because that would mean you would have to have a negative kinetic energy, if you think about it. You would have something here in the PE part which is larger than the E part here. And the only way that is possible for, for this thing here to be larger is if this thing here is negative. And of course, we can't have a negative kinetic energy. That doesn't make any sense physically to us. So classically, this particle cannot possibly get over this bump. It cannot possibly penetrate through the bump, get onto the other side, because it needs, more energy than we have given it here. We've given it this energy E, and in order to get over the bump, it needs at least energy equal to V0, but really, greater than V0. But it doesn't have that. But quantum mechanically, it is allowed to tunnel. This is the sort of rather incredible thing. So if we think about this from a sort of wave-like perspective, as we've drawn this wave function here, we're no longer thinking about, shooting a particle at this thing and seeing what it does after, because classically it should just bounce off. It shouldn't penetrate or do anything like that. But quantum mechanically, when we're dealing with this wave function, what actually happens is the wave function can penetrate, or the wave here can penetrate through the barrier. We can think about this, this is totally analogous to light coming into a transparent medium. So if you fire a ray of light at like a block of glass or something, some of the light will pass through the glass and will come out the other side, and some of it will be reflected off, this partial reflection you get. And this is more like geometric optics, but then if you change the angle the light is coming into the block, you can get smaller or larger amounts of the light reflected back at you. But the point is, some of it is reflected back, and some of it is transmitted through the transparent barrier. Like if you stand in front of a window, of course you can see through the window. Some of the light, is traveling right through, but also you can sort of half see your reflection when you look in a window, depending on the light levels and stuff. But that's an example of the partial reflection of your own image bouncing off the window, this transparent surface. And the same thing happens in total analogy to that with these wave functions. So with this wave-like property that these particles have, that we describe them with quantum mechanically. So now I've drawn the kind of snapshot that is happening during the instant where this wave packet is touching the barrier. So it's moving towards the barrier. There's some amount of penetration. So actually some of the wave kind of travels through the barrier. It actually, during this phase here, you can show that it exponentially decays. Rather than being like a wave, it will very quickly drop and decrease in amplitude. And then on the other side, we have this traveling wave emerging here. So this T I've labeled on this psi here is for transmitted. This is how much of the wave function is transmitted when it goes through. And then what I've called B here is the wave function inside of the barrier. Okay. And really this, the fact that you get some wave function here is really a consequence of continuity, in terms of continuity of the wave function as a function. So you can't have a discontinuous wave function in this way at a boundary. That is something that is not allowed. The Schrödinger equation, in terms of its boundary conditions, you can show that it should have a smooth solution to it. It should have a smooth wave function. So you have to have some kind of thing in here that will smoothly interpolate from this function up here. And another consequence, another thing you have to have, if the Schrödinger equation is continuous, which we say it should be, which I think actually you can physically understand that, the need for the Schrödinger equation to be continuous. I think this is a consequence of conservation of energy. I think if it had sharp peaks on it, it would... No, sorry, of conservation of momentum, I think. I think if it had... Oh, my iPad thought I was talking to it then. I think if it had sharp peaks in it, this would lead to sort of very large values of momentum, like in infinities in the momentum space. as far as I can sort of reason in my head, I think. So there are these two conditions on the wave function as a function. It has to be continuous, and its derivative has to be continuous at these barriers. So, here is one side of the barrier, here is the other side of the barrier. At both of these sides, these conditions must be fulfilled. And as a consequence of that, we have to have this sort of little portion in here, and also this little portion out here. So these sort of analytic properties of the function kind of tell us that there has to be some amount of wave function in the middle and on the other side. And of course, based on our understanding of what the wave function represents, the wave function, if you take its modulus squared, represents the likelihood of finding a particle at a certain position. What that means is that there is a non-zero probability of measuring the presence of an electron here. So if you start off with an electron here, as we denoted here by this wave packet, and you shoot it at this barrier, there's a non-zero probability sometime later that the electron will be found on the other side of the barrier, in this region which is classically forbidden. Because, as we said before, it's classically forbidden, as in order to get over this hump, there would have to be some time period where the electron has negative kinetic energy, which it cannot do. Physically, that doesn't make any sense. Okay, so we have some behavior here that is completely non-classical. It's uniquely quantum mechanical, this tunneling through this barrier. So this is during the kind of collision when, well, actually, I should also explain what these other things I've drawn here are. So this wave, this part of the wave here that I've drawn with the arrow going to the right, is the initial wave packet I had up here, moving in a rightwards direction. Then this thing down here I've called psi r. This is the kind of reflected component of the wave function that is bouncing off of this boundary. Just like how light bounces off the partial reflection I mentioned about looking through a window, in the same way. So this total wave function here is a superposition of this initial part from up here and an extra part that is bounced back from the left-hand side of the boundary. Then, as I explained, this psi b here is the wave function inside the barrier, which isn't zero because of continuity of the wave function and continuity of the derivative of the wave function. And then this piece on the right-hand side, which is also travelling in a rightwards direction, is the transmitted wave function. It's how much of the wave function gets through the barrier and is passing away now away from the barrier. Okay. So sometime after this, what we end up with is we end up with this packet here moving away from the barrier, and maybe I should get rid of this here. We end up with the packet moving away from the barrier, the transmitted part, and we have the reflected part moving away in the opposite direction to where it originally came from. Okay, so we've got some certain probability that there will be an electron found on the other side, which we wouldn't get classically. Okay, and we can do a calculation with this. So if you assume that rather than these kind of short wave packets I've drawn here, if you assume that you've got quite long wave packets that will, go on for a little while, so that there's a sort of continuous stream of the wave coming in, and therefore there's a continuous stream, in here, and also continuous stream out here, we can write down some equations for these different parts of the wave that are reflected, transmitted, and also the ones that are coming in initially. And we can write down equations that describe the fact that the wave function should be continuous and the fact that its derivative should be continuous. Okay. So I won't go into too much detail with these because they're not especially fun or interesting calculations. But so this is like at the instant in time that the particle is kind of colliding with the barrier, if you like. You can think about it in that way. So we've got this original wave coming in. We've got the amount of the wave that is transmitted through the barrier. Then also at this second barrier wall, as well as at the first barrier wall, we have some wave transmitted through and some of the wave function bounced back from the first side of the barrier. At the second barrier wall, you have the same thing, in that some of it is transmitted right the way through both ends, and some of it is bounced off on the interior part. So we have these 5 different parts of the wave that look like this. And like I mentioned earlier, it has to be the case that the wave function must be continuous at these boundaries, and also its derivative must be continuous at these boundaries. The fact that its derivative is continuous, I'm pretty sure you can show that as a consequence that the wave function itself is continuous at these boundaries. This is for a finite well, I should say. If you have an infinitely tall well, you actually don't need to have the derivative being continuous. There's actually a specific discontinuity in the derivative of the wave function in that case. But that's not particularly interesting. So now I replace these sort of psi's I've written here to represent the wave functions. I replace them specifically with actual wave-like solutions. And I've written these because it's most convenient in this complex exponential form, which if you... No, I should probably have explained this a little bit more, but if you know a bit about complex numbers, an exponential to an imaginary power is actually equivalent to a cosine plus an imaginary number times a sine. So it's very often that if you've got things that are wavy in some way, rather than writing them as sines and cosines, you can write them as complex exponentials, as I've done here. So a complex exponential traveling to the right, I've given with a positive power up here, and a wave traveling to the left has got a negative power for this complex exponential. Okay, and then the interesting thing that happens inside of here, inside of the barrier, this factor inside of the exponential power, so what is k here and what is b here, this is actually related to the square root of the total energy of the particle in green minus the potential it's traveling through. So here, this potential I've just set is equal to 0. So that means this k here is just proportional to the square root of the energy, this green energy here. But in here, you've got the green energy minus the red energy up here, which I called V naught, the top of this barrier. And this thing minus this thing is going to be a negative number. So I'm going to have, in this power k here, if you like, I'll have a square root of a negative number, meaning it'll just have an I in it. It'll have an imaginary part. And because there's already an I here, this thing now will have an I in it. When you're inside the barrier, this just becomes a -1. For the thing traveling to the right, anyway, it's a negative here. For the thing traveling to the left down here, it's a positive exponential. But these are no longer imaginary exponentials, or complex exponentials rather. They're just ordinary exponentials where b and x are both real numbers inside here. And then here we've got the transmitted amount of the wave, which has got the same k here because it's in the same sort of well on both of these sides, and it's traveling to the right. And then there's this kind of not too interesting algebra where you have to say that the total wave function on the left-hand side of this barrier is equal to the total wave function on the right-hand side of this barrier. So here I'm doing like a superposition. I'm taking this top right moving part of the wave, which appears here, and I'm adding it onto the bottom left moving part of the wave that is here. And I do the same thing on this side, this part, on here, and here. And I say these things should be equal because the wave function should be continuous at this boundary. It shouldn't go like here and then jump up here. It should be continuous there. So whatever it is just to the left of the boundary should be the same as what it is just to the right of the boundary. And I do the exact same thing to get this equation, but now it's the right-hand side of the boundary over here. And then I do the same thing, except now instead of thinking about the wave function psi being continuous, I think about the derivative of the wave function d psi by dx being continuous. So what I would do is I would add up these two things here on the left, then differentiate them with respect to x, and set that equal to adding up the right-hand side here, differentiating that as well, and set those things equal to each other at this boundary, and do the same thing on this boundary. So I get 4 equations, and I've got 1, 2, 3, 4 unknowns, so you can solve this completely. A and B are things you already know from the Schrödinger equation. If you input your guessed solutions for the waves back into the Schrödinger equation, you get what K should be and what B should be. Are the resulting solutions to the Schrödinger equation analytically solvable or only numerically? Yeah, there are lots that are analytically solvable. This one is analytically solvable, for example. So, certainly when you go to higher dimensions, so like 2 dimensions or 3 dimensions, and you have much more complicated potentials, then things get a lot more difficult. But in fact, a really important example of the Schrödinger equation being solved is for the hydrogen atom, which you can do analytically. So if you think about what the simple 1D Schrödinger equation we have here looks like, where we just have it in 1D, and I've got this potential Vx, which for us is quite simple, it's just this well here. If you think about what the Schrödinger equation would look like for a hydrogen atom, say you're trying to use psi to describe is the wave function of an electron going around the nucleus in a hydrogen atom. Well, then the potential that the electron feels is a Coulomb potential. So, like in Coulomb's law, the force between 2 charged particles is proportional to 1 over the distance between them squared. Well, that means that the potential energy of that system of 2 charged particles, the potential energy they have, is proportional to 1 over the distance between them, just 1 over the distance without a square. So you would have a 1 over distance in the potential, but then of course, if you're thinking about an electron going around an atom, you have to think about this in 3D because, our universe is 3D, so thinking about what the hydrogen atom looks like, you'd only really want to do this in 3D. In 1D, it wouldn't really mean anything. In 2D, it would be ridiculous simplification. So everything will now be in 3D. So not only will I have derivatives in X, I will also have derivatives in Y and Z to encode the fact that this will be a 3D system. But this Schrödinger equation describing the hydrogen atom would be totally solvable. You can solve it. It's a 2-body problem. If you've got, a nucleus and an electron, you've got 2 bodies, well, a proton and an electron, because a hydrogen nucleus is just a single proton. If you get more complicated than that, so say you try to solve something like helium, that is actually not exactly solvable. That is very difficult. Well, it's not very difficult actually, but it's a lot more difficult than hydrogen. And then if you try to go to something like lithium, where you've got 3 electrons and 1 nucleus, that gets really quite difficult. That's like a 4-body problem. Whereas helium is a 3-body problem, and you probably know in physics you can't analytically solve 3-body problems. You have to do them numerically. So in terms of atoms, hydrogen is exactly solvable and gives you some very powerful and important results. Helium is not, and helium and anything up is not analytically solvable. But you can solve it pretty well, through perturbation theory to get good numbers out for helium. You can do that by hand on paper. For things maybe bigger than helium, you probably couldn't do it by hand. It would be too difficult. I'm not sure though. I'm not a chemist, so I don't know. Oh, hello, Zwei. I am back indeed. Good to see you. So yeah, that was a note about whether this thing is analytically solvable. So we go through all this algebra, which is actually, I don't think, too interesting really. But the point is we get to a result here that tells us the probability of the particle making it through to the other side. This transmission amplitude, as it's called here, this capital T omega squared. But it's an expression you can find analytically. I challenge anyone to sit down and actually do it. I fully admit that I copied this result from a textbook because I couldn't be bothered to derive it. It's not very pleasant. But it's perfectly doable. You've got one equation, two equations, three equations, four equations, and four unknowns. And the one we're most interested in, the unknown we're most interested in, is t that appears here and here. So you could easily, well, not easily, you could feasibly do it if you wanted to solve this equation and rearrange for t. Or you can just trust that the author of this textbook, and I've forgotten which one I looked in now, has got this reasonably correct, in that this would be the probability of your particle being transmitted through this classically forbidden barrier. So I guess that's kind of a little glimpse at quantum tunneling. There's certainly more I would like to say about it, because tunneling it's an important thing in my research actually. Though this is that's more tunneling in quantum field theory, and made more difficult by the fact that it's tunneling in quantum field theory in a curved space background. So you have these fields present in the space-time. The fields affect the gravity, so they affect the curvature of the space-time. The curvature of the space-time affects how the fields propagate and how the fields will tunnel, and the probability of them tunneling from one minima to another. So it's a really complicated, strongly coupled system. Not one we can solve analytically either at the moment, though there are potentially some hopeful avenues by which it might be solved analytically. But I mean, if we knew that, I would get my PhD tomorrow, but we don't know that, so we've got no idea. But that would be an interesting problem to solve. So I definitely like to talk more about that perhaps another time. But for now, actually, I kind of want to talk about some of this stuff that's been going on with muons, which is definitely very interesting. In the last month or so, we've had two pretty big announcements. The first one from LHCb talking about lepton universality. So how there's actually appears to be, well, I can't remember what the significance is now. I think it's 3.1 sigma or something. 3.1 sigma, that electrons and muons, so these two different families of leptons, appear to couple differently to the weak interaction, which is not something that is predicted by the standard model. The standard models, an important thing that appears in the standard model is lepton universality, that electrons, muons, and taus should all couple the same to the weak interaction. But this data from LHCb appears to contradict that, and it appears to contradict it quite significantly, in that in this particular decay they're considering, which I think is B mesons to K mesons, there is something like there's like 0.8 times the chance that you get a muon coming out the other end than there is that you get an electron coming out the other end. So, that's a significant deviation. It should be that the chance of an electron coming out the other end, when you consider this decay of a B meson. So, well, maybe I should write it down a bit. So this is, let's call this, I don't know, muon news 1. So I can't remember when this date was. It was like, approx 3 weeks ago. That's how behind I am with streaming. It was around 3 weeks ago, I think. And this is this RK measurement, I think they're calling it. And what they've done, what this measurement is doing, is they're looking at how B mesons decay into K mesons or kaons. So it's about positive B mesons decaying into positive K mesons, and when this happens, you also get an anti-lepton produced and an ordinary lepton produced. So these are L's here. I realise my L's sometimes look a bit funny, but I promise these are L's. And the theory tells us, so the standard model theory anyway, tells us that it should be just as likely that you get an electron and an anti-electron. Oop, I didn't mean to circle that in black. The electron and the anti-electron, I should say, coming out, as it is likely that you get a muon and an anti-muon coming out. These should both happen roughly the same amounts. If you do this experiment 100 times, or maybe 1,000,000 times would be better. If you do it 1,000,000 times, 500,000 times, you should get a muon coming out, and 500,000 times, roughly, you should get an electron coming out. This was a Suez Canal meme result. It was probably around that time, yeah. I missed all those. Well, I didn't miss them all, but we didn't talk about any of those Suez Canal memes because that was a while ago. Yeah, there were some good memes about that, though. It was around that time, I believe. I don't think I actually saw a Suez Canal-themed Muon RK crossover meme, though. Maybe I did. I can't remember. I definitely saw some physics Suez Canal memes, but I don't know if there was a specific one about the RK result. I'm not sure. So this is the thing they were measuring anyway. They were looking at the decays of B mesons into kaons. So a B meson has got, I think it's an anti-bottom and an up quark that make it up. A kaon is then an up and an anti-strange quark, and then these leptons, this could be e.g. a positron and an electron, or the contrasting case they were actually comparing with here, or an anti-muon and a muon coming out the other end. And what you expect from the standard model is that if you do this experiment 1,000,000 times, like I say, half the time you should get a muon coming out the other end, and half the time you should get an electron coming out the other end. But that's not what they found. They find that it's more like 0.8 times. Well, rather, it's the chance of getting a muon to come out the other end is 0.8 times the chance of getting an electron to come out the other end, which is something that is not predicted by the standard model. In the standard model, the only difference between muons and electrons is that muons are a bit heavier. Well, actually, quite a lot heavier. Is it like 200 times heavier or something? I'm not sure. They're quite a bit heavier anyway. But there's no difference in the standard model anyway, in the theoretical basis of established particle physics, that muons and electrons, or muons, electrons, and tau particles should behave any differently to one another. But this measurement seems to... It is 200 times. Okay, great. This measurement seems to show that they do actually behave a little bit differently, which is interesting because, of course, if the measurement is confirmed, at the moment I think it's only 3.1 standard deviations, and the kind of golden standard in particle physics is a 5 standard deviation, 5 sigma result. If it gets to 5 sigma when they get more data or do other measurements or measure things in different ways, that would be big news. It would tell us that there's some physics going on that is not described by the standard model. The theory behind these decays is, I think, is so solid that it wouldn't really be possible that there's some theoretical muck-up. The only way this result could be wrong... Well, sorry, what I should say is the theory is so solid within the standard model, in that if the experiment is to be trusted and it gets to 5 sigma and it confirms that there is this difference between the different families of leptons, between the electron and the muon, then it would signify some beyond the standard model physics, distinct from what we have already today in the standard model. You wonder if the high luminosity upgrade will allow this result to be tested more accurately. I mean, I'd expect so. I expect that's probably why, one of the reasons they do these upgrades is to get high luminosity, higher, more collision rates, more data, more decays per second, etc. I don't know. I mean, I'm not a experimental particle physics person by any stretch. I'm barely even competent with the phenomenology side of it, but experimentally, I don't know much about that. I don't know how easy it is to produce B mesons, or how many they can produce, by doing these collisions in LHCb. So I don't know. I assume, higher luminosity, it certainly makes sense. Higher luminosity, you just get more data, I would expect. That's probably one reason why they're doing it. Well, it's probably the reason why they're doing it. So there are some ideas about. So that's the experimental side. The experimentalists have measured this discrepancy between the chance of getting a muon to come out the other end and the chance of getting an electron to come out the other end. I should maybe write down why this is called RK. It's called RK because this kaon branching ratio, as it's called, is about 0.8. Actually looked at the paper. The paper says it is where is it? There it is. So the paper says that the RK they measured, it's about 0.8 something, but what is it specifically? They say 0.846, and then it's a 3.1 sigma measurement. So what that means is if you're doing this measurement, you're measuring these decays of B mesons into kaons. The chance of a muon coming out the other side compared to an electron coming out the other side is times 0.846. So the chance of a muon coming out is 0.846, the chance of an electron and a positron coming out the other end. Hello, Jegchin. That's an interesting emote there. So that is what that says. That's the experimental side. And there are some ideas. Again, I think in the paper, actually, they do some nice plots. I'll tell you what the paper is because I think it's, well, I mean, depending on your... As a non-experimentalist person, I found it fairly reasonable to read. It's HEPEX 2103.11769. If you type that into Google, you'll get, the archive page for this paper will come up, and you can take a look at it. So they draw these two diagrams. So really, the thing, if you notice in what I wrote here for the B meson and the K meson, the only difference really between the B meson and the K meson is this change of a bottom quark or a beauty quark. Personally, I prefer bottom quark, of a bottom quark or an anti-bottom quark rather, to an anti-strange quark. They both still have an up quark in common, so that doesn't really change. So you can kind of summarize this decay by the Feynman diagram that they give on the page. So they show this Feynman diagram like this. And I'll explain what some of these things mean in a minute. And then they've got in here, it's either an anti-up, an anti-charm, or an anti-top. Then they've got, this is either a photon or a Z0 boson. And then they've got the lepton and the anti-lepton coming up here. So this is the Feynman diagram they give for the standard model process that shows the decay of a B meson, of a bottom quark into an anti-bottom quark into an anti-strange quark. So these different parts here, so where they've got, where they've written anti-up, anti-charm, and anti-top, that is because this is really shorthand to save them drawing what would actually be like 6 different diagrams. They draw them all like this. So the reason it's 6 different diagrams is because this particle here, that is, coming along this line of the Feynman diagram, it could be an anti-up quark, it could also be an anti-charm quark, and it could also be an anti-top quark. So all of these three different channels, as they'd be called, will contribute. And likewise, this boson down here, it could be a photon or it could be a Z0 boson. Both of those contributions will, those things will contribute. So you've got three choices up here for which quark appears in this propagator in here, and you've got two choices for which boson appears down here. So that's a total of 6 choices. So there are 6 diagrams contained within this one standard model diagram. And one of the other things, these kind of speculative theory things they give that might explain why the muon is less likely to be produced than the electron, is the existence of a new particle that they call a leptoquark. I think it's a leptoquark, or is it a lepton quark? No, it is a leptoquark, that's right. So the diagram for that is like you've got your bottom quark here, then instead of having the W plus boson as we had above, you've got this new particle called a leptoquark, and then there is the anti-lepton and the lepton produced in this way. Oop, that arrow should go the other way. Don't worry too much about the directions of the arrows. If you don't know about Feynman diagrams, it doesn't really matter. The point is, you've got your bottom quark in this kind of speculative potential model will decay into a anti-lepton, like a positron or an anti-muon, and also into this new particle, this hypothetical particle called a leptoquark. And the reason they've called it a leptoquark is that quarks are particles that interact by the strong force. They can interact with other quarks in that way. And leptons are particles that interact by the weak force. And this leptoquark particle, if it exists, would interact by the weak and the strong force. In sort of this way here, it will carry quark-like and lepton-like information. But again, there's no verification at all that these new particles exist at all. It's just one possible theoretical explanation for this experimental result, that muons are less likely to be produced in these particle decays than electrons are, when really they should be equally likely. In the standard model, this RK here should exactly equal 1, meaning that electrons are just as likely to come out the other end as muons are. But it doesn't. It turns out it's slightly less than 1, actually. It's 0.846, and this with a 3.1 sigma reliability to it. But again, we can't get too excited about it because it's got to wait until it gets to 5 sigma. And I think there's not been any other verification using different experimental techniques. But then I suppose that's not too important because these are pretty well trusted experimental techniques. But still, we shouldn't get too excited until it gets to 5 sigma. But it is exciting, as in the sort of physics that could underlie what is going on, what it would signify. But we'll have to wait and see. So that was the first piece of muon-related news, this RK result. And then there's the more recent news that is about the G-2 measurement. So this is muon news 2, I guess. And this is the G-2 measurement. So this G here is in kind of classical, well, not classical, I suppose, but in like sort of Bohr level quantum mechanics, this G would be exactly equal to 2 for all spin-half particles. And it basically tells you the ratio between the spin of the particle, measured in units of h bar, I think, and the magnetic moment of the particle. So how strong, how strong a magnet, little bar magnet this particle is, because, of course, electrons and muons, all these other particles that have spin, act like little bar magnets. So this G factor is just a sort of numerical factor that translates between, or is one of the things that translates between the spin of the particle and how strong this little bar magnet is, the magnetic moment of this thing. And what the result that's sort of come out a few weeks ago is from Fermilab in, is it in Chicago? I mean, I know it's in Illinois. I don't know if it's exactly in Chicago, but I think it's in Chicago. It's in Illinois, certainly, anyway, in the United States. And they've measured a value for this magnetic moment, which disagrees with the main accepted calculated value. So you can calculate the value of G using quantum field theory. It's a very difficult calculation, and it's one that, I think a paper was released. I think the paper was released last year that had like over 100 different authors on it. That was like a big, really certain, or very obviously well verified. It had over 100 authors. Very well trusted theoretical calculation of what the muon G factor should be. And then this new data from Fermilab appears to contradict that predicted theoretical value. And it appears to contradict that with a reliability of, 4.2 sigma, I think. So this is more significant, but still not quite at the 5 sigma golden standard, but it's more significant than the 3.1 sigma for the RK measurement anyway. So that's why all these pop science articles said it would open up some new physics. Yeah, exactly. Both of these things, in theory, might open up some new physics. I don't know, my understanding is that the muon, the RK measurement, the original piece of news we were talking about, is the more exciting piece of news. The reason being, this second piece of news about muons, the one that is more recent, it was like a week ago or something, about the G-2 result. There's another paper. So there are two papers that are theory papers, two theoretical calculations that are claiming to have calculated the G factor of the muon. So they've tried to calculate this G-2 value. The reason it's G-2, like I said earlier, is that if you were to do this, just with like the kind of Bohr atom or something, it would be... Oh, thank you, Your Environment, Seattle, for following. That's nice of you. The reason it's G-2 is that if you were looking at this thing like just the Bohr atom, without any quantum field theory corrections, it would just equal exactly 2. So the -2 part is kind of looking at the correction from quantum field theory on top of what is classically expected anyway. So that's why it's G-2. So there are these two theory papers. There's one that's like a year old from this big consortium. I can't remember what it's called now. Theory something starts with an I. I can't remember. Theory Initiative, I think. So it's like over 100 researchers on it, and they've calculated a value for the G factor, and this is the value that is at odds with the more recent measurements that have been taken. And the way they've done this, the way they've calculated it, is very different to this second paper, which is a lot more recent, which came out, about a week ago, pretty much the day, I think it was the day before the data was actually released from Fermilab. So there are two papers. The first paper from a year ago with like 100 plus people, the Theory Initiative one, that is the one that appears to be at odds with the data from Fermilab. But the way they've done the calculations in this paper is they've taken, I don't understand it all, to be honest. A lot of this comes from my reading of what other people have said about it, because like I say, it's not my area. This stuff is quite detailed, very difficult calculations that are outside of my area, so I've not looked into the extreme detail of them. But essentially what they're doing is they're sort of adapting calculations you would do for an electron. Say you were trying to measure the G factor of an electron. They've taken what those calculations would look like, and they've converted them into muon-like calculations, what you would do if you were looking for the muon. But then rather than actually do the electron calculations, what they've done is they've got data from, taking experimental measurements of the electron G factor, which we have much more reliable measurements than we do for muons. Because it's harder to get measurements for muons because they decay quite quickly. They're heavier than electrons, so they don't live as long. So we've got very good data for electrons. So what they've done is they've taken these calculations, or the calculations you would have to do for the electrons, and they've converted them into the calculations you would have to do for the muons. But I don't think they've actually done those parts of the calculations. They've kind of sandwiched in the data, the experimental stuff we have already about electrons. Because electrons are, we've got good data on them, because they're easier to do these measurements with. So the muon G-2 have taken a non-standard approach. Well, as I say, I don't know if it's non-standard or not, because it's not really my area. I think it's a good approach. I think people have a lot of faith in it, and this is a very large theory collaboration, so I'm sure that they've worked out all the details very carefully, and it's all very kosher, very reliable. I don't know if it's standard. I don't know if a similar approach has ever been taken before, because this is not within my area, but certainly this is the first I've heard of such an approach that I can think about. But that means that in no way means that it is a non-standard approach. I couldn't say whether it's non-standard or not, to be honest. But it's not the only approach. So the other approach has been taken by these other theorists. That I think this paper, I keep seeing it referred to as the BMW paper, and I think that comes from the names of the universities of some of the places. But I looked at the names of the universities on the paper. I've got it up here actually somewhere. Yeah, that's it. Budapest, Marseille, and Wuppertal. But there's also other universities there that don't fit into that at all. Like there's one in Germany I actually can't pronounce, and I don't want to offend Sly, so I won't try and pronounce it. Jülich or Forschungszentrum, and then also University of California, San Diego. So I mean, these are not B's, M's, or W's. Oh, you're studying at one of the involved departments. Oh, that's interesting. Wuppertal is the German university. Are you studying at Wuppertal, or one of the different ones? Oh, Jülich is a research center. Ah, I see. Oh, you're at Wuppertal. Oh, cool, awesome. Yeah, I imagine. I'm sure you do enjoy that in a kind of sadistic way. I'm not very good at pronouncing German words, or any other words really. What was I saying? So yeah, so there's this second paper that is called, I think, the BMW paper. People have called it because, as Yang said, based on the places, or some of the places anyway, where these researchers are coming from. But there are other places on there that are not captured by B, M, or W, but it doesn't really matter, I guess. And they've done this calculation in a different way. So one of the most difficult parts of this calculation is the fact that there's a kind of hadronic part that affects the muon's G factor. So all these corrections, these kind of 11th decimal places and whatever, are all corrections that come from quantum field theory, and quantum field theory calculations are not easy to do. And in particular, quantum field theory calculations that involve hadrons, things like mesons and baryons and whatever. These things are even more difficult. The strong force QCD is difficult to work with. So they have tried to calculate the contribution from QCD based on something that is called lattice QCD, which is like a numerical technique for solving, for doing QCD calculations, which I really know very little about. It's something a lot of people are working on at the moment. It's quite complicated, and as well as always, it's not quite my area, so I don't know a great deal of detail about it. But it's it's a numerical um, technique and set of sophisticated techniques for doing QCD calculations using very powerful supercomputers and stuff like that. So they've done this calculation in that way using some supercomputer. I don't know where the computer's based actually, or where they are based. Um, and they've come up with a different number for the G factor. I can't actually remember the numbers now. And the paper was fairly... It wasn't actually obvious to me where they stated these numbers. But again, this is coming from what other people have written about it. And what I've seen other people writing is that this more recent paper that came out like the day before the data came from Fermilab actually doesn't really show a discrepancy between the theory prediction and the data prediction. They're kind of within error bounds of each other. You believe the calculations performed on many supercomputers, some of them based in Jülich. Oh, okay, right, fair enough. Yeah, I was thinking actually as I said it, it's probably not just a single computer, is it? It'll be, things different, dividing them and doing them in different places and all sorts of very difficult computational things. That's interesting though. So yeah, so the second paper, they don't find a disagreement with the experimental result. So this is kind of, it's turned into like a theory versus theory problem. There's one group of theorists from this big, I've forgotten what the word again, the theory starts with an I, initiative, was it initiative? Theory initiative, that have said this is in disagreement. This data is in disagreement with the theory we've worked out. And there's this other group of theorists also, it was initiative. Okay, great. There's this other, oh, I just realized I didn't drink my tea. Oh, it's like totally full. Oh well. Oh, now it's just cold. Bugger. Oh well. Yeah, there's this other group of theorists that say actually it's not different to the experimental result we found. Oh, hello, Matthew. Good to see you. So it is interesting. Personally, I'm more excited by the first piece of news about the lepton non-universality, because that seems more to me like, I mean, it's more obvious that would be a big problem, like a big breakdown of the standard model that would sort of immediately indicate beyond the standard model physics, whereas the G-2 thing, there's a slight uncertainty about it that it may just be a calculational issue, because these calculations are very, very, very difficult. But it could also indicate beyond the standard model physics. Certainly, supersymmetry, if it exists, will have an effect on the G factor of a muon, and the G factor of all the particles you get in doing these calculations. If you add in supersymmetry, you get loops of supersymmetric particles in these Feynman diagrams that will affect the G factor of the muon. So this could indirectly be a way of, measuring the presence of supersymmetric particles, or this discrepancy could be a result of supersymmetric particles, but probably not. It's probably I don't know. My relatively uninformed bet is that it's a calculational issue. And either way, it's only at 3.1 sigma at the moment, so no need to get too excited. Or is it 4.2? I've forgotten which one is which. I can't remember which one is 4.2, which one is 3.3. This one, okay, it's a 4.2, so actually it's more significant than I thought. The one I'm more excited about is the less significant statistically, is 3.1 sigma. But actually the one we're just talking about now, the G-2 one, that is like 4.2 sigma, I think. So that is, to be fair, that is quite on the way to getting to 5 sigma. We'll see. Slice says, string theorists going wild right now. Well, yeah, I mean, I don't know about string theorists, but I looked on like the morning after the G-2 announcement, opening up the archive, looking on the HEP phenomenology section, there was just like tons of papers. Some involving supersymmetry, like I mentioned just then, but really all sorts of stuff about the G-2. just like a flood of them. I didn't read any of them, I'll be honest. I'm too busy reading different papers right now, and I think probably I wouldn't understand a great deal of them anyway from these new influx of papers coming in. But it is a really interesting time, and it's also particularly cool that these things came in. They're both about muons, and they both came in within the space of a couple of weeks of each other, which doesn't happen particularly often. It was pretty exciting to see the work my advisor and other professors I know being involved and talked about so much recently. Yeah, I bet that is really cool. Yeah, that is awesome that you kind of know some of the people that are on this BMW paper. Yeah, that's awesome. Yeah, it is a really exciting time. We could look at some memes, I guess, couldn't we? Haven't done that in a while. Obviously, feel free to chuck any more questions that are coming to mind in the chat, and we'll chat about those too. But for now, let's look at a few physics memes. Oh, what's this? Hossenfelder will be very angry with all these strings talks. She seems to get worked up by them. Ah, yeah, I do follow her on Twitter. She does seem to get, I don't know, she seems to get angry at a range of different things. I haven't particularly noticed about string theory stuff. The most recent beef I saw on science or physics Twitter was about Neil deGrasse Tyson tweeting something about, oh, science is true. And you had all these people being like, no, science is not true. It's like it's an effort to re-establish truth at every stage and follow evidence, and empirical evidence to sort of approach truth, but never quite settle on something as being absolutely true, because you can't really have absolute empirical evidence, I guess. So a lot of people were kind of annoyed at that, but I mean, I don't know. I think it was a lot of fuss about nothing, really. I got the point that he was trying to make, that it was probably not very well worded, but then Twitter is full of things that are not very well worded because of the character limit and the slightly sort of regurgitative nature of it anyway. But I think what he was probably getting at was just that, if you're trying to establish things that are true, or, establish things that are true within some reasonable range of uncertainty, the scientific method is the only real way to do that. There's no other real way to approach truth using any kind of other system of thought or logic. You can only have empirical evidence, which is really, well, I was going to say is unique to the scientific method, but I suppose it's not unique to the scientific method, but is most, perfectly exemplified by the scientific method. You bought her book Lost in Math. That was really funny. I haven't read that. I read her blog, and I watch her YouTube videos and follow her on Twitter, etc. I do think she's really good. She writes really nicely and writes some really interesting, cool stuff. People under Neil's tweets are always really weird, and they think they know everything better. Yeah, I think it's that sort of. You get a lot of that on like his Twitter, Richard Dawkins' Twitter, which, to be fair, is problematic for a number of other reasons beyond the kind of people that you have in his replies. All that sort of science popularizing sort of fairly new, well, not that new, but sort of modern intellectual scientific, slightly kind of atheist science popularizers. They have sort of a group of maybe slightly arrogant followers sometimes. I wouldn't want to generalize, but I'd say that can sometimes be the case. But that's the case among anyone. You can't judge people too harshly on the people that find them interesting. Certainly in science, it's important to be humble. And sometimes these people don't come across too humble. The followers, I mean, not so much the people themselves, though you could argue that, but I won't comment on that. You attended a talk of her once, and it feels like she raises some really good points, but sometimes she seems a bit confrontational. Fair enough. Yeah, I don't know. I don't know if I describe her as confrontational or not. I'm not sure. I haven't. I'm not a close enough follower or things like that. To make comment on it. Fringe science. Yeah, I'd guess so. I guess I'd call it that. Um, Not sure if it's the right word. I get what you mean. I don't think it's. I don't think it's an insult. I think it's a reasonable criticism. I just don't know if I would. I don't know if I have enough experience to make a similar criticism or equally to dispute that criticism. So we've covered both the big physics stories in the last 2 weeks, but forgot to cover geometric unity. Yeah, there's a reason for that. In that I think it's been pretty well debunked. Um, well, not debunked, but there are legitimate criticisms of it. And the weirdest thing was when I was reading through, I read like the manuscript, and like Eric Weinstein has kind of he put a bit in it that is like he copyrighted this work in his name and said something to the effect of no modifications building on this or um, work related to this without the consent of the author would be allowed and stuff. Which I mean is that's totally bizarre in science. That's not how science works. You can't copyright the framework of an idea and forbid someone to build on it or start correcting it. He actually sort of outlined you couldn't do corrections. I don't know legally how that works, if there's any standing to that, or if there's any way it could be enforced, or any way you could find a judge or an impartial mediator that has sufficient knowledge of high energy particle physics that they would be able to distinguish between what would be covered by him copywriting that or alleging to copyright that, and what is fair use or whatever. So I don't know if reasonably that could ever be enforced, but that's what he did anyway. He wrote in the thing, which I thought was very odd. I mean, a lot. I haven't read the thing in detail, the actual paper. I watched the talk he gave, because this all spanned from a talk that he did in Oxford. Not, I didn't watch it in person. He did it in Oxford. I think maybe it was before I was there in like 2014 or something. I can't remember when it was. When he was invited by Marcus de Satoy to give a talk to like the particle physics group in Oxford, like the theoretical particle physics group in Oxford. And I watched that talk, but I don't know. I'll be honest, I didn't follow a great deal of it. It's all about it's all about geometry and spinners and higher dimensional stuff, and it's I don't know. I'm not sure. I think there was some criticism of it sort of immediately after the talk, saying that these extra particles that were kind of implicit in what he was saying would have been detected by now, and there are some more sort of sophisticated theoretical problems with it that I saw somebody raise on Twitter. But as I say, I can't comment on specifically what I think about it because I've not looked at it in enough detail, and frankly, it's probably, for the moment, it's a bit above my pay grade, above my head. But it's interesting nonetheless. I mean, and some very respected people, very good physicists, thought it was worth listening to, and that there were some interesting ideas there. But I think him as a character and the way he has kind of presented it is a little bit atypical. But I think I suppose he acknowledges that it's totally atypical because he's not a scientist. But sometimes he comes across a little overly proud of the fact he's not a mainstream scientist, and I think perhaps a little unduly critical of mainstream science or whatever, mainstream physics, whatever that means, and it can be a bit dismissive of a lot of things that shouldn't necessarily be dismissed. He has some ship in a bottle operator, but apparently forgot how it works. But yeah, that's another thing. There is this big disclaimer at the front that sort of says this is something he did a long time ago and he's kind of forgotten how it works. Which, I mean, is fair enough. I forget, if I read a paper a month ago, likelihood is I've forgotten the majority of it, particularly the subtle points of it, but more likely the vast majority of the most glaring points. So I do have complete sympathy with that aspect of it. You watched the 2013 one, but he was on Joe Rogan last week, his buddy, and I decided to give it a miss. Yeah, he's been on Joe Rogan a couple of times, I think. I've not really watched. I don't really watch Joe Rogan, but I think I may have watched part of the episode he was on. I also watched the episode because Roger Penrose was on Joe Rogan. I watched that one. That was quite good. But then it was good because Penrose is on it, and Penrose is very interesting to hear talk anyway. The best bit is at the end of the paper. It says Weinstein is not a physicist and no longer an active academician, but is an entertainer and host of the Portal podcast. Yeah, I'd say that's a fair summary of, I suppose, his role. I've never heard anyone referred to as an academician. He used a few things like that in the paper, I seem to remember, which were like non-standard terms for groups of people and stuff, like academician, or there was another one as well, I seem to remember. I can't remember what it was exactly though. But yeah, that was somewhat physics news, somewhat interesting physics news, I suppose. He has lots of Hebrew, I think. Ah, I see. I didn't make that link between. I'm not sure which Hebrew things you mean in there, but okay. I'll try and spot them again if I read through it. Not that I know any Hebrew, really, or at all. Anyway, I guess let's look at a couple of memes. And then let's absolutely keep chatting, though, if there's more stuff. And I need to remember to drink my tea before it literally freezes over. It's already completely room temperature. But it'll do. Someone in chat should remind me every couple of minutes to remind me that I have tea. I'll have to do that. At the start of the next stream, I'll appoint a dedicated tea monitor who has to remind me that I have tea next to me. And I'll give you, I don't know, what can I give people for being a tea monitor? Channel points or something? I don't know quite how that stuff works. I'll try and figure it out. Someone can have the role of tea monitor next time. So let's look at a couple of memes anyway. Let me... Ooh. Okay. Now, has my audio screwed up? No. Cool. Okay, right. So let's look at some of these. Oh, thank you for the cheer, Matthew. That's very nice of you. Okay, yeah, meme. What am I doing? My brain just did not focus for a minute. I receive your life. You receive two Nobel Peace Prizes, radium and polonium. Oh, poor Marie Curie. She did get very ill from doing all that research. Well, I mean, she died actually. I think it killed her. Maybe redeem rewards as drink tea. That's not a bad idea. I could do that. But really, it's like the tea is a reward for me. So it's like you'd be spending a reward to give me a reward for tea. Whereas really, I should be giving you a reward for reminding me to drink tea. But I don't quite know how rewards go backwards in that way. I don't know. Who knows? We'll think of something. It's a good suggestion. Keep the suggestions coming if you think of any. Also, this meme format, I'm so sick of it now. It wasn't really funny when I first saw it, and it's still not funny now. It's a reward for me if it's warm. That is very true. If it's cold, it's at best damage control. At the moment, this is just damage control, because this tea is, you know, it's basically completely cold. Still tastes good, though, but cold. For the WLM March and Rally, it says we wear a mask for anonymity. Why would they want anonymity? Maybe it's because they get cancelled if they're maskless. Oh great, now we can't... Oh, they misspelled maskless. Now we're cancelling photons. Fair enough. No, you couldn't skip the Coulomb barrier. Your energy is below the energy of the barrier. Tunnel effect. Want to see me do it again? Oh, this is related to the tunneling stuff we were talking about today. That's actually another important example of tunneling. Like, I think we talked about it actually when we were talking about the insides of stars a while ago. That you couldn't have fusion inside of stars you couldn't have fusion inside of stars without quantum tunneling. It just wouldn't work. The temperature inside stars is not hot enough to get these nuclei close enough together that the strong force takes over. In order to get them close enough, they have to actually tunnel through the Coulomb barrier, the repulsive Coulomb barrier between them, which is exactly what this meme is talking about. Yeah. He's got a bow tie and glasses as well. He's got a slightly different haircut to me, but hopefully I'll have a... Oh, subscribed at tier 1. They've subscribed for 2 months. Oh, cool. That's I don't know really what that means, but thank you very much. That is nice. I'll have to try and think of a way of changing the tier or something. You can so you can make me, well, not make me drink tea, because drinking tea is obviously very nice. I'll think of something. I'm not sure. Very open to suggestions. Now you're finally in my Discord, so you can let me know there. Ah, hello Velocity Fright. Good to see you again. We are currently looking at memes, but before this we were talking about muons, the various types of news that's been related to muons after I've been away for the last 3 weeks. And before that we were talking a little about tunneling. You have to get us subs more emotes. Yeah, that is very true. At the moment, you basically only have the one of me looking slightly weird with the sunglasses on. I should definitely look into some other ones. I mean, I would be very happy for suggestions. This is a good suggestion. More emotes, definitely. I will see what other ridiculous pictures of myself or ridiculous physics pictures I have. I mean, there are lots of ridiculous pictures of me, to be honest. I think most pictures of me are ridiculous pictures. But anyway, so that was a good meme. But yeah, as I was saying, this guy's had a haircut. Hopefully, I will also have a haircut by Friday. That would be nice. Exactly, that face there, the Cosmic Bob one. What a lovely face. Well, not really. What a lovely emote, I mean. Cosmic Microwave background, I don't know. I'm not Hubert Reeves. Cosmic Microwave, nice. That's a good one. Billy, what have you done? Physics is the same as math. Shoot him again, Billy. Very true. Very, very true. Analytical mechanics go brr. This was linear momentum a few years ago. This is him now. Feel old yet? Oh, that reminds me of that video I put in the Discord, which was... Who is it by? Who is the guy that did the video? There was a really funny video about momentum the other day. Oh, that was it. Eigen Chris. They did a video about momentum. I'll put it in here too, because it was a very funny video. It just reminded me of that, though, about... Oh, wait. Oh, no, that's a link to a channel, not a link to... Ugh. I'm a moron. I can't even copy the link to this. What am I doing? Copy link. There we go. Right. There's the link to the video. That's what I meant. That video, what is momentum? Exactly, that's it. That was a funny video. That was good. Whatever, I won't watch that. It's called audio. And also it's got Jordan Peterson in, so I definitely won't watch it. Any book by Griffiths, page 1 introduction, page 2 the end. What? I don't get it. Griffiths books aren't short. Does anyone, any aficionado of Griffiths textbooks understand that meme? Because I actually don't. No clue. Oh well, fair enough. I mean, to be fair, it looks like only 7 people got it anyway. No slander on Griffiths. Definitely, I absolutely love Griffiths books. His electrodynamics one, the particle physics one, those are brilliant books. I want to die. I want to reach the state of thermodynamic equilibrium. Oh, okay. Is it possible for spin-zero particles to travel faster than light when tunneling? No. Nothing can travel faster than light when tunneling. There isn't superluminal tunneling. I think there's no real reason to presume that it will happen. I think so. At the start of the stream, I spoke a little bit about things that kind of appear superluminal in quantum mechanics, but actually aren't. Not specifically related to spin-zero particles. But no, tunneling doesn't happen faster than the speed of light in any kind of meaningful way. In the same way that, like I mentioned at the start of the stream, if you have entangled particles, it kind of appears to be that you're extracting information about one of the particles that may be potentially very, very far away from you, such that that information is traveling faster than the speed of light. But it's not sort of useful information in the sense that you could communicate anything with anyone. You couldn't encode a message in this sort of entanglement. So no, tunneling does not go faster than the speed of light. The Twitter page Meme Crashes is my go-to for math/physics memes. So good. I will take a look at that. Thank you. Meme Crashes. I will take a look. Thank you, definitely. So it turns out a squirrel would need to fall about 4,800 miles in order to die, because that would give it time to starve to death because they can survive terminal velocity. Rachel, I'm begging you, it's 2:30 in the morning. That information is on a need-to-know basis. Wow. That is an incredible fact. I mean, that fact about squirrels is interesting enough as it is, that actually squirrels don't take fall damage because, they're so light, but their area is big enough that they reach their terminal velocity is not fatal to them. So you could drop it from as tall a building as you like. Once it reaches terminal velocity, which is its maximum speed, it won't go any it won't go any quicker, and it won't splat. It'll survive. Yes, Boltzmann statistics. It's Usain Bolt. Nice. And a Boltzmann curve. Interesting. Hard to swallow pill. Math is more fundamental than physics. I determine the volume of a sphere by assuming it is a cow with radius r. That's one perspective to take. But also, I don't know if math is more fundamental than physics. One of my first year lecture I had for quantum mechanics was talking, about whether he thought what was more fundamental, math or physics. Certainly, maths can describe lots of physical situations that are not realized in nature, and therefore I suppose it generalizes physics in that sense. But he seemed to think it was perfectly possible that physics might one day break down and give you logic out of it, or the different laws of physics, so totally abstract, might give different sort of logic procedures and different kinds of mathematics to them. But I don't know. I never really had much faith in that. Logic and set theory from philosophy. No, yeah, that's my understanding too. You have kind of logic and stuff like that sort of set up axiomatically, and that builds to gives you different builds on more mathematics on top of that. But certainly it's not a case that I don't think it's as simple as physics is applied maths. There is a distinction between physics and maths. It's sort of there's a lot of interesting questions there, about what will we ever run out of maths? Are the laws of physics that our universe kind of plays out, are they beyond mathematical reasoning? I mean, mathematics as we use it is really kind of a crutch to aid our understanding. When you say you understand something, or you understand why something will happen, you do it by a calculation. That calculation acts as a crutch to sort of intuition, is my opinion. So there are some things you can kind of reason intuitively about what will happen, but there are some things you can't reason intuitively whether they will happen or how quickly they will happen, etc. The mechanics of that. And that is where, maths is a crutch to aid that limit in our understanding. Our brain is not programmed. Our brain is not even programmed to really understand certain Newtonian physics calculations. It's sort of practically wired in that we know, without doing detailed projectile motion calculations, roughly how hard to throw something and what angle to throw it at to get it to a certain place. We know how to throw a rock at a monkey in a tree, that we can knock it out and eat it or something. This is obviously an important evolutionary skill, that we have these sort of calculations, if you like, inbuilt to us. But we have no such physical intuition for things like quantum mechanics. quantum mechanical scattering, there is no physical intuition where you can kind of think about a wave packet coming in and say, oh, well, what will the amplitude be at this position on the other side of a slit or whatever. There's no physical intuition to that. There's only mathematical intuition. Sometimes, mathematical intuition can leak into physical intuition if you think about it enough and get used to the maths enough. But I think they're quite different. So it's an interesting question about whether or not we'll eventually run out of whether this mathematical crutch will reach its limit and will reach some physical thing that the universe knows how to, that God knows how to calculate to make it happen in the universe. I use God there with a small g, as, in the sense that Einstein said God doesn't play dice, not God as in any literal theological construct. Whether the universe knows how to calculate these things such that they happen, whether we can match that with our mathematics. It's an interesting question. I don't know the answer. Well, no one knows the answer. Will it run out? Will it not? Is the physical universe a subset of the mathematical universe, or are all the different possible mathematical universes that describe different kinds of laws of physics, are they all subsets of our particular physical universe, in that they are describable within the mathematics we have in this universe, but there are potentially other realms or whatever where there is different mathematics or less or more mathematics that describes other physical realities, possibly including our own, possibly not. Wow, that's a real ramble. I promise I haven't taken any drugs. This is just how we're thinking about maths at the moment. David Hilbert is a wonderful example of... Oh, sorry, wait, what was that? Hang on, I've got a few things to read. Squirrels have been gifted by square cube law. That's very true. Yeah, their terminal velocity is proportional to the square of their size, their area, and I guess their splatability maybe is proportional to their cube. I don't know how would you determine whether something... I suppose it is like a cube over square thing. The square is proportional to the area, which is, if you've got a large area, it's easier to splat something. And if you've got a large volume, there's more stuff to splat. No, that doesn't quite make sense. Yeah, I'm not sure how the physics of splatting squirrels works exactly. Poor squirrels. I don't really want to think about that. I saw a squirrel today on the campus, which was really cute, but the cutest thing I saw today was a tiny little baby rabbit running down near the co-op on the campus here, which was very, very sweet. It was so tiny, I don't even think it really knew that it should be afraid of humans, so it just kind of sat staring at me for a while, which was very nice. But anyway, David Hilbert is a wonderful example of how both are very deeply intertwined. Read his wiki page if anyone is bored. Okay, so David Hilbert and meme crashes. I've got some homework to do to look up these things. This is great. The universe is one big neural network. I guess that's one way to look at it. I'm not sure what I think about that. That sounds interesting. Corporate needs you to find the difference between these two pictures. They're the same picture. That is very true. What is that symbol even called? Is it it's not Xi, is it? Or is it Zeta? No, it's not Zeta. I can't remember. I think it's Xi. Yeah, that's it. Yeah, Chi or... Oh, Chi, exactly. Yeah, Xi, Chi. Yeah, I really struggle to draw that one. Absolutely. That is what mine looks like. Definitely. Life is good. F equals ma, but it can be better. Exactly. Always Lagrangian mechanics over Newtonian mechanics. 100%. Capital is the 3 horizontal... Oh, yeah. The one that's a long line, shorter line, longer line. Zeta is the wiggleless one, right? Yeah, like the Riemann zeta function, where it's essentially this one, but without the middle bump here. So it just goes round, and then you cut off this bump, so it'll go down, it'll go round like that, and then down at the bottom without the middle bump. That's zeta, I think. I always forget the names of the letters. Yeah, me too. When you see an engineer running through the physics department, get the rat. Nice. Sorry, theoretical physicists. When studying, you remember 10% from reading, 25% from hearing, 35% from seeing, 50% from seeing and hearing, 75% from discussing, 85% from experiencing, 95% from teaching someone else. Well, how can you experience? I can't experience string theory. I can't see string theory. I can't hear string theory. What am I going to do? Well, just not understand string theory. I don't have to understand string theory, fortunately. Just replace the symbol with gamma or beta to make the notes look pretty. That is true, to be honest. I often end up replacing my letters with slightly more simple ones. My friend's talking about quantum physics. Sleep is just a time regime to breakfast, my dudes. I mean, that's very true. Who would win? A badass clinical psychologist? I don't know about badass personally. Clean your room. One thermodynamic boy. Entropy always wins. You can't beat entropy. Physics grade. Physics professor grading be like 16.712899 out of 20. Fair enough. Oh, hello, non-dairy neutrino. Good to see you. Oh dear lord, they're in on it. When the Chi resonance baryon is thus. Dun dun dun. Nice. 2 equals 3. Of course. My lecturer used this as an introduction to thermo on their first day. I like him. But I can't read it. Can I read it now? Whoa, that did not increase the icon size. Ludwig Boltzmann, who spent much of his life dying. That what? Did you say studying statistical mechanics? Died in 1906 by his own hand. Paul Ehrenfest carried on his work, died similarly in 1933. Now it is our turn to study statistical mechanics. Wow. Yelp. A history of suicide in statistical mechanics. That does not bode well. Fortunately, I think I managed to just about survive my undergrad statistical mechanics class. Wow. Look at those slippers. Einstein was a fashion icon. The classic intro to StatMech. Yep, the classic. Are you back teaching now, or are you on break? I am. Well, I think the undergrads here are on a break until. Oh, actually, I think this is the first week of term, isn't it? I think this is the first week of term, but because of the way it works, so the undergrads will have lectures this week, and then I do some like tutorial problem class teaching. So they'll have like problem classes set this week, but it won't be till next week that they'll start having the tutorials and the classes to go through the problem sets that they're studying. So it won't be till next week my teaching actually starts. But I've only got a couple of weeks because I think this term, well, it's not even really a term. I need to get out the habit of saying term, because I think the university here and most universities in the UK use semesters. So instead of, in my undergrad, we always had like just 3 terms, but most universities do 2 semesters. So this current part we're in is like, the second part of the second semester. So it's a continuation from the semester I was already doing some teaching on. But a lot of this second part is just them doing their exams. So the teaching will end after a couple of weeks. So I've only got 2 weeks of teaching. Then I will be relatively free, which will be nice, to do more kind of researchy stuff, which will be fun. You only got 3 weeks left till your finals start soon, and you can apply for uni. Wow, yeah, that's coming around pretty quickly. This time of year it always starts ramping up a bit. Luckily I have no exams though, for the first time in like, what, 10 years? With like high school, university, well no, not 10 years, like 8 years, 9 years or something. A long time anyway, if you think about from GCSEs at like 15 or 16 to now. It's been a long time since I've not had an exam, which is a nice feeling. So I definitely feel sorry for you, Sly. But luckily I don't have any for myself. Hey, I just met you, and this is crazy. Now I'm a particle, so call me maybe. Fair enough. Interesting Hawking radiation meme. You just finished an 86-page summary on the topics of your physics class for your physics finals. Wow, that's quite a lot of pages. So are you going to take the exams like usual? Will you take them in school, or will they be like online exams? How will it work? Will they be online open book, or will they be online like invigilated? Like, I think I heard that Imperial College in London did that last year, where I think they had online invigilation, where you had to put your camera on and have someone like staring at you while you're doing your exam, making sure you're not looking at your phone or anything, which sounds absolutely horrible. Luckily, mine last year were just open book ones, but because they were open book, the examiners made them relatively horrible, but it was okay. Quantum Festival, how nuclear energy works. I can't bother to look at that. That doesn't look like a meme. Dark wobble. Wait, what? Where are the memes? Okay. Oh, it'll be in school like usual, but you'll have to wear masks, lots of distance between the tables, and maybe we'll have to do these COVID tests. Okay, well at least that sounds safer. That's good. Student, I don't understand. Teacher, well, you are stupid. I don't understand. Indian man on YouTube, I will teach you, my son. That is true. There are a lot of really good, like, education channels talking about physics and other things that are run by, I do see lots of Indian teachers doing them, which is really, really great, really nice of them. If you're bored, you can simply close your eyes and rotate a cow in your mind. It's free and the cops can't stop you. But because the cow is spherically symmetric, it looks the same. This person doesn't know that cows are spherically symmetric. Terrible. How does Hawking temperature increase as the black hole evaporates? Does it? What is the Hawking temperature again? What is the formula for it again? I've forgotten. It does increase as the mass of the black hole decreases, doesn't it? It's like a 1 over the mass in there. How does it increase? How does it decrease? How does it increase, sorry? What's the way to understand it beyond just the fact that it's kind of a calculation you do? I'm not sure, really. I'm not really sure if there is a straightforward way to understand it. I mean, as the mass decreases, the area decreases, meaning the entropy of the surface is smaller than it was before. So that would mean the temperature has got to be hotter if the entropy of the black hole is increasing, you've got to kind of put more thermal energy out into the universe to increase the entropy of the universe, so you don't violate the second law. That's not really a very good explanation, but I'm not sure. Certainly it follows from the calculation, like the sort of slightly cheaty calculation we did a couple of weeks ago about black holes. Your physics final is on the 6th of May, so about 23 days. Wow, I can't believe it's already mid-April. It's almost May, really nearly May in like 2 weeks' time. Pretty crazy. Really excited. It's a weird feeling being almost done with this stage of your educational life. Yeah, finishing high school is definitely an exciting time. Hopefully it'll all be back to normal when you start university. That would be really great. Physicists measuring the speed of light. C equals 1. Always use natural units. Always. The other person. Wait, give me a moment. Me. Moment of inertia. Nice. Oh, there's a dog. I didn't even realise there was a dog in the background of the picture. Wow. Friend, I want to study string theory. It's so cool. The ogre has fallen in love with the princess. Is the person that wants to study string theory the ogre and string theory is the princess? I think that's what it means, but I don't get it. Fair enough. Haters will say it's fake. Comic Sans for extra spice. 1 over sine x. What? Is equal to 1 over x dx. Since sine x is approximately... Oh, that's disgusting. How dare they? You can't do that. Disgraceful. There's no accountability anymore. Adiabatic. A diabetic. A diabetes. Nice. You might take some radiology rotations just so you can play with our cyclotrons. Oh, that's cool. Ah, so I was wondering what the MD in your name meant, if it meant like medicine. So I take it from that you are kind of into, you know, medicine, doctory, well, an MD or training to be an MD or something. That's interesting. Yeah, definitely. Playing with particle accelerators sounds pretty cool. I mean, it sounds better than actually being near human patients, to me anyway, but I'm a massive, like, I can't deal with blood and guts and things like that. That really freaks me out. Nothing really matters. Sounds about right. Nice. We study non-perturbative instabilities of ADS space-time. Oh, that actually sounds pretty interesting, to be fair. Instantons and bubbles, that's somewhat related to what I'm interested in. Studying some high-end physics like it makes no damn sense compels me, though. That sounds about right. Me learning Gauss's law for the first time. Yeah, that makes sense. Yeah, I can see that. Double closed integral. Fair enough. Physicists, fusion, deuterium, tritium. Sounds about right. Sorry, libs, I deal with conservative forces only. Oh, that's, oh, what's his name? Ben something. Can't remember his name. Quite a weird guy. Ben Shapiro, that's it. Thank you, Vandil. Yeah, strange guy. Well, I think I might leave it there actually, chums. It's 9 o'clock now, and I'm feeling relatively tired. It was the first time going to the gym today since like November, October time when the lockdown started. So quite achy and want to sleep relatively soon. But if you missed any of the stream, then feel free, you can catch up with the VOD afterwards. If you haven't already, feel free to join my Discord. And then I'll see some of you guys on... Wait, what day is it? What day is it today? Today's Tuesday. On Thursday. Thursday for some Mario Kart. And more physicsy chat. But yeah, thanks a lot everyone for coming along. Thank you for all of your wonderful chats and interactions. It's been lovely as ever, and good to be talking to you guys again. I've definitely missed talking to you all in the last few weeks, so it's been really lovely. So yeah, join the Discord if you like, and I'll see some of you on Thursday. Okay. Bye everybody. Bye 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 bye.